Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 10 on derivatives.
We're about to begin Chapter 2 on differentiation. Now, you may know how to compute some derivatives, but do you know what they really mean? In this lesson, we'll distinguish between the interpretation and the definition of a derivative. And by the end of the lesson, you'll be seeing derivatives everywhere.
In your introduction to calculus, you probably learned derivatives as slopes. Well, you may be surprised that we have not talked very much about slopes in this course thus far, and that's because slope is an interpretation of the derivative and not what it really means. It is not the definition. In fact, it's a pretty poor interpretation. For example, when you go to multivariable calculus, you're going to look at functions with multiple inputs and multiple outputs. What does a derivative mean for that? Let's say you have a vector field, or you're looking at a digital image that consists of many, many variables. Or worse still, you're looking at functions that aren't smooth enough to have a well-defined slope. In all of these contexts, derivatives make sense even when slopes do not. We'll consider three different definitions of the derivative. The derivative of f at x equals a is, first, the limit as x goes to a of f of x minus f of a over x minus a. This might not be the definition that you recall seeing, but it's a great definition because you can interpret it as the limit of the change in the output over the change in the input as the input tends to a. This definition, among all of the definitions, is to me conceptually the clearest. You have an input and an output, and as you change that input at a certain rate, the derivative tells you at what rate the output is changing. Our second definition should look familiar. The derivative of f at a is the limit as h goes to 0 of f of a plus h minus f of a over h. This, too, has the interpretation as the limit of the change in output over the change in input as the change in input, h, goes to 0. Of course, this is really the same definition. We've simply performed a change of variables, setting h to be equal to x minus a, the change in the input. If you substitute x minus a in for h above, writing x as a plus h, then you'll see that this is really the same definition. Our third definition is a bit different, and it's in terms of the first order variation of the output. What do I mean by that? Well, consider your function evaluated not at a, but at a plus h. What is that equal to? Well, it's f of a plus some perturbation term, some variation term that depends on h. We say that the derivative of f at a is the constant c satisfying f at a plus h equals f at a plus c times h plus other stuff that is of higher order in h. That is, big O of h squared. This constant in front of the first order term is what we can define the derivative at a to be. Now, this is not the definition that you are used to seeing. In fact, there are some problems with this definition. Some people call this a strong derivative because sometimes it does not exist, even when the true derivative in terms of a limit does. For purposes of this course, we're not going to worry about that distinction so much, thinking in terms of a Taylor expansion and using the language of big O to control higher order terms is going to wind up being very illuminative. Let's compare these different definitions in the context of a simple example. The simplest one I can think of is f of x equals x to the n for some positive integer n. In this case, the first two definitions of the derivative of f at a are of the form limit as h goes to 0, f at a plus h minus f at a all over h. Knowing that f is really raising to the nth power allows us to simplify a bit. What happens when we take a plus h and raise it to some positive integer? Well, the first term is going to be a to the n. The next term is going to be n times a to the n minus 1 times h. This comes from the binomial theorem, or multiplying out as a long polynomial. What about all of the other terms? I may not have room on the page to write them all, but I know that all of them have powers of h that are at least quadratic. I'm going to compress all of that together and call it big O of h squared, which is exactly what that is. And now we see a perhaps familiar computation coming about. The a to the n terms cancel, and everything that is left has some power of h. We can factor that, cancel with the denominator, and we obtain the limit as h goes to 0 of n times a to the n minus 1 plus some terms that are in big O of h, so that as h goes to 0, they vanish, and we are left with the familiar computation of the derivative of x to the n at a. Now, it's worth observing that really that definition of the derivative is the same as the third definition in terms of the variation of the output. If we take our function f and evaluate it at a plus h, what do we get? A plus h to the n. This has a constant term, a to the n, a first order term, n times a to the n minus 1 times h, plus higher order terms in h. That coefficient, the first order term, is the derivative at a. A few other examples will help illustrate this. Let's look at some familiar functions, e to the x, cosine of x, and square root of x. First of all, for e to the x, let's compute the first order variation by evaluating it at x plus h. Now we know that e to the x plus h is e to the x times e to the h. And although this is a little bit of circular reasoning, we know what e to the h means. That's really 1 plus h plus terms of higher order in h. So if we expand this out, we see that the constant term is e to the x. The first order term in h is e to the x times h. All other terms are higher order in h. And from this simple computation, we can see that the derivative of e to the x is e to the x. It's the coefficient in front of the first order term in h. Likewise, for cosine, what happens when we look at cosine of x plus h? Well, we can use the summation formula for cosines and expand this as cosine of x times cosine of h minus sine of x times sine of h. And again, using what we know about cosine and sine, we can expand the terms in h and say that cosine of h is 1 plus big O of h squared, and sine of h is h plus big O of h cubed. Now, if we take these terms and rearrange them a little bit, we get a 0th order term of cosine of x, as we must. The first order term has as its coefficient in front of h negative sine of x, the derivative of cosine of x. For the square root, we have to simplify the square root of x plus h. How do we do that? Well, if we factor out a square root of x, what is left over is 1 plus h over x, all to the power 1/2, or the square root of it, if you like. I write it in this form so that we see the binomial series come into play, and using that binomial series gives us an expansion of 1 plus 1/2 times h over x plus something in big O of h over x quantity squared. Now, if we expand that out, we see that the 0th order term in h is, of course, square root of x. The first order term simplifies to 1/2 x to the minus 1/2 times h. And from that, we see the derivative. Now, notice that all of the higher order terms involve a square root of x and something in big O of h squared over x squared. If we want to ignore that and call that big O of h squared, we'd better make sure that x is positive. When x is 0, we have a problem. The derivative does not exist. But as long as x is bounded away from 0, we have a well-defined expansion in terms of h, and we can read off the derivative as 1 over 2 square root of x. There's a lot of notation associated with derivatives. The derivative of the function y equals f of x can be denoted in the following ways. Some of the best notation is df dx or dy dx. But there's some other notation that you might see or use from time to time, including f prime or y prime or y dot. Now, why the difference between these? Well, the best notations are those that tell you exactly which variables are changing. dy dx means the rate of change of y with respect to change in x. On the other hand, f prime or y dot can be a bit ambiguous. The dot in particular connotes change with respect to time. Sometimes you'll see a differential notation of the form df. This can be helpful, but again, remember which variables are changing. The one thing that you must never do is write something foolish like canceling the d's to get df dx equals f over x. Whew, no way. Don't get creative with your handwriting on these. Don't use a scripty cursive D. Don't use a Greek delta. Don't do anything like that, because those symbols have meanings of which you have not yet learned. Don't ever do any of this. Stick to the standard notation, please. Now, the most common examples of derivatives wind up involving rates of change with respect to time. For example, in your introductory physics, you've certainly seen velocity or acceleration as a derivative. These are derivatives of position with respect to time. But there are other examples as well. If you study current, current is related to a rate of change of charge with respect to time flowing through a wire. In chemistry, if you look at reaction rates in a chemical reaction, these are defined as the derivative of, say, a concentration of a product or a reactant with respect to time. There are many other examples of derivatives that are not necessarily rates of change with respect to time. If you look at a spring, one can define the spring constant as the rate of change of the force applied with respect to the deflection. The elastic modulus of a stretchy material is a rate of change of stress with respect to strain. If you want to know what viscosity is, or how slippery a fluid is, well, this is defined in terms of quantities like shear stress and the rate of change of the velocity of a sliding fluid with respect to height. And finally, economics consists of all manner of interesting derivatives. For example, if you look at marginal tax rates, these are defined as the rate of change of the amount of tax collected with respect to change in income. All of these are wonderful examples of derivatives.
There's so much more to derivatives than slope. Look around you. Do you see something that changes? That is a derivative. Derivatives are ubiquitous, and understanding their proper definition helps us to interpret, find, and then use derivatives. In our next lesson, we'll consider how to quickly compute derivatives.
Welcome to Calculus. I'm Professor Geist. We're about to begin Lecture 11 on differentiation rules.
From your previous exposure to calculus, you probably learned how to compute derivatives quickly without the definition by following a certain set of rules or laws. We're going to cover those rules in this lesson. Such a topic has the potential to be boring, but pay attention because we're going to cover why the rules hold, and in doing so, we'll get a better grasp of the notion of a derivative.
Recall from our previous lesson that we had two different ways of defining the derivative. One is in terms of a rate of change. It's a limit as the input approaches A, the change in the output over the change in the input. Our second definition, a little bit stronger definition, is in terms of first-order variation. One changes the input to f by a small amount, h, and looks at how the change in the output depends upon h. If you like, it's the coefficient of the first-order term in the Taylor series of f at a. From these definitions flows the interpretation of the derivative as the rate of change of the output with respect to change in the input. And this is the interpretation that you will want to have memorized. A few remarks are in order. First of all, the derivative, as you know, most certainly depends upon the input value, A, that you are examining. Secondly, a derivative concerns rates of change. We're not actually measuring how much the output changes. We are looking at the rate of change as the change in the input is getting closer and closer to zero. Lastly, the derivative at A is telling you a rate of change. It's telling you how fluctuations or changes h in the input are perhaps amplified if the derivative is positive and larger than 1, or damped if the derivative is, say, less than 1, or reversed in the case where the derivative is negative. That is a good interpretation for the derivative, one that will serve you well in this course. Now, there are several rules associated with computing derivatives. I'm going to present these rules compactly using a simplified differential notation that you're familiar with from your previous exposure to calculus. The first rule is that of linearity. This consists of two parts. First, what you might call a summation rule, that the derivative of the function u plus v is the derivative of u plus the derivative of v. The second part of linearity says that if we multiply u by a constant c and take its derivative, what we get is that constant c times the derivative of u. The second rule, the product rule, states that the derivative of the product of two functions, u and v, is u times the derivative of v plus v times the derivative of u. Lastly, and perhaps most importantly, the chain rule states that the derivative of a composition of two functions is the product of the individual derivatives. We'll have some more to say about that in a moment. For now, let's focus on the rules of linearity. The summation rule can be visualized rather simply. Keeping track of how u changes and how v changes, and keeping track of how u plus v changes, is really not that difficult. Likewise, when you multiply u by a constant, what happens to its rate of change? It is similarly scaled. That picture is at least reasonable. There's another way to think about these rules as well. This is a way that I often think about it. If you take the sum of the two functions and then differentiate, it's the same as differentiating the pieces and then adding them together. Or likewise, you can multiply by a constant and then differentiate, or you can differentiate and then multiply by a constant. Whichever path you travel, you will get to the same place. These pictures illuminate, but do not really justify, the differentiation rules. To do a better justification, let's use our definition of the derivative as a first-order variation and employ the language of big O. First of all, u plus v evaluated at x plus h means what? Well, we take u evaluated at x plus h and add to it v evaluated at x plus h. Now, by our definition of the derivative of u, we know that the term on the left is u plus the derivative of u times h plus something in big O of h squared. Likewise with v. Now, let's rearrange this sum by ascending order of h. The zeroth order terms are u plus v. What are the first order terms, those that have an h? Well, on the left we have du dx, and we add to it the term from the right, dv dx. Everything else is something in big O h squared plus something in big O of h squared. That is in big O of h squared, naturally. So we see that the first order coefficient is the sum of the derivatives, as expected. Likewise, when you multiply u by a constant, c, and evaluate that at x plus h, it is simply c times u plus du dx times h plus something in big O of h squared. The zeroth order term is c times u, the first order term is c times du dx times h. Everything else is a constant times big O of h squared. But remember, in big O, constants don't count. And so we see that the first order term, the derivative, is c times du dx. Likewise, for the product rule, it's not hard to visualize the first order variation of u times v in terms of du and dv. But to write this out using our language of big O is very simple. If we take u times v and evaluate it at x plus h, that is u at x plus h times v at x plus h, we can substitute in the expansions for u and v and perform this multiplication. If we multiply these terms as if they were polynomials, what do we get? The zeroth order term is simply u times v. All of those terms that are of first order in h have coefficients u times dv dx plus v times du dx. Everything else in that multiplication, as you can check, is going to be in big O of h squared. And so the derivative can be read off from the first order term, and we get the product rule. Lastly comes the chain rule. This is perhaps the most important differentiation rule, and it deserves a little bit of exposition. The chain rule concerns the composition of two functions, u composed with v. That means you do v first and feed the output of v into the input of u. Now, what do the rates of change, what does the derivative look like in this case? Well, dv is telling you at what rate the output of v changes with respect to change in the input. Du tells you at what rate the output of u changes with respect to change in the input. What is the derivative of the composition? Well, it tells you when you change the input to v at a certain rate, at what rate does the output, the final output of u composed with v, change? And the answer, as one can intuit, is that these rates of change multiply. The justification of the chain rule is going to follow the same ideas, but with a bit more manipulation involved. If we consider u composed with v and evaluate the input at x plus h, then clearly our first step should be to expand out v using what we know about the derivative of v with respect to x. Everything else in the variation has big O of h squared. Now, let's change perspective and think about this from the point of view of u, which takes as its input v. Now, we're evaluating u not at v, but at v plus some perturbation, some variation term, which we know has the structure of dv dx times h plus something in big O of h squared. Forget about that structure for the moment. We're going to expand this out. The zeroth order term is u of v. Next comes the derivative of u with respect to v times this perturbation term plus something in big O of that perturbation term squared. And now, here comes the final steps. If we look at that big O on the right and view it as a function of h, then, squaring everything in sight, we see that everything has powers of h that are at least 2. And so we can replace that by a big O of h squared. Now, for the terms in the middle, when we distribute the multiplication of du dv with all of the terms in the parentheses, well, the latter term, du dv times something in big O of h squared, yields, again, something in big O of h squared. And so, combining those big O's of h squared, we are left with a first-order term in h that has coefficient du dv times dv dx. And that is the proper form of the chain rule. Now, one has to be careful. The differential notation is especially misleading at this point. You must evaluate your derivatives at the correct inputs. Let's look at a simple example. Let's say that f of x is the exponential function, e to the x. What is the derivative of f composed with itself? Well, according to the chain rule, it should be df dx times df dx. Well, that's not exactly what it is, because we have to be careful about the inputs. If we were to say, evaluate this derivative at x equals 0, then the second term must be evaluated at x equals 0. The first term in this product is evaluated not at x equals 0, but at x equals e to the 0, or 1. That would give us a value of e times 1, which is, of course, e. Now, this looks awfully confusing. What's really going on? Well, you know how to differentiate functions, and you know how to use the chain rule. Let's think about what f composed with f is. It's really e to the x. And if I were to ask you, how do you differentiate that? You would say, well, first, I differentiate the e to the x and evaluate that at e to the x. That gives me e to the x. But, because it's the chain rule, I have to multiply by the derivative of that exponent. In this case, e to the x. Now, if you evaluate both of these at x equals 0, you get the same computation as above, with the final value of e. Be careful about where you evaluate your derivatives. There are a number of other differentiation rules that you may have seen in your previous exposure to calculus: the reciprocal rule, the quotient rule, the inverse rule. If you remember seeing these, then take a brief look. If you've not seen them before, then you might want to work through the following examples, such as showing that the derivative of secant is secant times tangent, or that the derivative of tangent is really secant squared, or that the derivative of log of x, that is, the inverse of the exponential function, is in fact 1 over x. I'll leave it to you to take a more careful look at some of these rules and to practice in the homework sets.
And so we see the basic rules for differentiation. But wait, there's more. If you look at the bonus material, you'll see how some of the ghosts of these rules haunt other realms of mathematics. In our next lesson, we'll cover one of the canonical applications of derivatives to linearization.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 11, Bonus Material. In our main lesson, we covered the basic rules for differentiation. Now, the question comes up, why spend so much time on those rules? You might think that it is merely so that we can do computations more easily, more efficiently. And although that's very helpful, there are other reasons why you want to know these rules. Mathematics, and indeed the sciences, are full of interesting patterns, and sometimes you'll find something you recognize hiding within a very different looking system. Knowing the rules helps you recognize patterns. We're going to take a look at two examples of this from very different fields. We'll begin by looking at spaces, or geometric domains on which you might do calculus. Examples would include a simple interval, or maybe a circular disk. Now there's an operator that is not unlike differentiation, but it acts on spaces as opposed to functions. This is the boundary operator, and we denote it with a scripty sort of D. What does the boundary operator do? Well, it gives you the boundary of a domain. For example, the boundary of an interval is simply the two endpoints. The boundary of a circular disk is simply the circle that is at the edge or boundary of that space. Now, there are other operations that act on spaces as well. For example, there's a way to multiply two spaces together in something called the Cartesian product. For example, a rectangle can be considered as the product of two intervals. Or a circular cylinder can be considered as the product of an interval with a circular disk. That would be a solid three-dimensional domain. Now, you might guess that there's some interesting mathematics contained inside of this product. For example, the disk is two-dimensional, the interval is one-dimensional, and this cylinder is three-dimensional, 2 plus 1. I wonder if that pattern continues. Well, let's consider what happens when we compute the boundary of a product. What is the boundary of a rectangle? Well, it consists of the edges along the boundary of the rectangle, of course. But we can think about that in terms of the product structure. This boundary is really the boundary of the first interval times the second interval. But we also have the other edges as well, which can be viewed as the boundary of the second interval times the first. We need to add these together. This is done through taking a union of those two sets of edges. Seems as though there's something I've seen before hiding within that boundary computation. Let's see if the same thing works with the cylinder. If I look at the boundary of this cylinder, then what does it consist of? It consists of the two end caps, which is the circular disk, cross the boundary of the interval. But it also has the side that wraps around. That is the interval times the boundary of the circular disk. If we take the union of those collections, we get the boundary of the cylinder. It is a fact that if you have two spaces, A and B, you take their product and compute the boundary of that. You can decompose that boundary as the boundary of the first space times the second, union the first space times the boundary of the second. Now, where have you seen something like that before? That's really a product rule, but we're not differentiating anything. We're simply computing boundaries. This gives you a hint that there's some deep relationship between differentiation and boundaries. That relationship will be fully exploited when you get to the end of multivariable calculus. Let's consider another example, a completely different setting. This time, working in computer science and looking at lists. Let's say that we have a list of objects. Let's say they're all the same type of object so that we call them X. So a list of 5 items would be X, 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 X. Let's do some mathematics. Let's combine those together and call that list X to the 5th. That tells us there are 5 elements. Now, how do you take the derivative of a list? Well, that doesn't make any sense, but there are some things that we can do. Consider the following deletion operator, D, that acts on a list and deletes one of the items. What is D of this 5-item list? Well, you could delete the first item in the list, or you could delete the second item, or the third, or the fourth, or the 5th. Now, each of these is really a list of 4 elements. So we would call it X to the 4th. One way to encode this logical OR is to use a formal sort of addition. We'll just call that plus. That means OR. So deleting a 5-item list gives us one of 5 different 4-item lists. We could say more compactly that D of X to the 5th is 5 times X to the 4th. And this is something that should look familiar. I wonder if there's something deeper that we can do with this intuition. So let us denote by X to the n a list of n elements. What would X to the 0 be? Oh, that would be an empty list. You have no items in your list. But instead of calling that X to the 0, let's call it 1, like it ought to be. And consider the collection of all finite lists. We'll call that L. Let's do some calculus. Here's a statement. Any list is empty or it has a first entry. I hope you'll agree that that's intuitively true. What does it mean in this language that we're constructing? Well, any list certainly means L. That's our collection of all finite lists. What does it mean that it could be empty? Well, that means that it could be 1. What does OR mean? Oh, OR is our formal addition. So L is equal to 1 plus, and here's the tricky one. What does it mean to say that a list has a first entry? Well, that means it has an X in it, followed by something, by some finite list, maybe empty, maybe non-empty. We can rewrite this statement as L equals 1 plus X times L. And now, let's do some algebra, see what comes out. If we move all of the L terms over to one side and factor out that L, what happens when we solve for L and get an expression for all finite lists? Well, as you can clearly see, L is 1 over 1 minus X. What in the world does that mean? Well, we know what 1 over 1 minus X really is in terms of the geometric series. What does that mean? Well, in this language we've constructed, you can read this statement as saying that any finite list is empty, or it has 1 item, or it has 2 items, or it has 3 items, or 4, or 5, etc. And so we see yet another interpretation for the geometric series. Now, some students are surprised by this example, that you have derivatives and Taylor series coming up in a more computer science context. Well, that shouldn't be too much of a surprise. Mathematics is full of patterns that can describe all sorts of things in the natural world. If you're interested in learning more about some of these unusual examples, the first, concerning spaces, comes from the subject of topology. The second, concerning lists, comes from the subject of analytic combinatorics. Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 12 on linearization.
Derivatives are useful in so many contexts, moving far beyond computing slopes. In this lesson, we'll cover one of the primal applications to linearization. This stems from our understanding of Taylor series. Linearization is the first step in a Taylor series, using the first derivative to approximate.
Thinking of derivatives in terms of linear variation can be frustrating if you're trying to visualize it. It's maybe not so easily visualized as is slope. However, in some examples, you can really see the variation. Consider the area, A, of a square of side length x. What happens if we increase x by a small amount? The area becomes x squared plus 2xh plus h squared. We can see those terms by increasing the side length a little bit and decomposing the extra area into a pair of rectangles with area x times h and a small square whose area is h squared. So ignoring the terms in big O of h squared, we see that the linear variation is 2x times h. For a triangle, we would get something similar. Let's say a right triangle with length x and height x. Then the area, 1/2 x squared, has the following variation. A of x plus h is 1/2 x squared plus x times h plus 1/2 h squared. Visualizing the additional area, we can break it up into a parallelogram whose width is h and whose height is x, giving a linear variation term of x times h. The leftover material is in big O of h squared. Lastly, for a circular disk of radius x, we have that the area is pi times x squared. What does the variation look like in this case? A of x plus h is pi x squared plus 2 pi x h plus pi h squared. That means if we increase the area a little bit, then the first order term has area 2 pi x times h. But then you've got this leftover higher order term. How does that work? That's a little harder to see. It's maybe a bit easier if you approximate the circular disk by a regular polygon with many sides and extend those sides out to a height of h. Then you see that there are a number of small triangles left over whose areas will add up to that of a disk of radius h in the limit as the number of sides is going to infinity. These first-order variations are the basis for doing linear approximation. For example, let's say you want to estimate the length of a banister for a staircase. If you know something about the dimensions, let's say it's 13 units across and 9 units high, then that length would be square root of 9 squared plus 13 squared, or the square root of 250. Let's say you want to come up with an estimate for that. I don't know what that exact number is, and let's say I don't have a calculator. Well, I could consider the function f of x equals square root of x. And I do know what the square root of 256 is. So that's 16 squared. To get from there to 250, I could use a value of h, a perturbation of negative 6, so that from a Taylor expansion, f of 250 is going to be f of 256 plus, well, the derivative evaluated at 256 times the difference times h, negative 6. All other terms in the Taylor expansion are of higher order. Well, let's see. Square root of 256, that's 16, minus 6 over 2 times 16. That gives us 15 and 13 sixteenths as an answer. And that's not so bad of an approximation. That's about 15.8. The true answer is the same up to the first 3 digits. So in this case, linear approximation works pretty well. Consider a different example. Let's try to estimate pi raised to the 20th power without using a calculator. Here's a hint. If you look at pi squared, that's pretty close to 10. It's roughly 9.86. I'll let you do the math without a calculator to verify that one fact. Having done that, let's consider the function f of x that raises x to the 10th power. And then, if we Taylor expand that function about x equals 10, then we're not too far off of pi squared to the 10th, or pi to the 20th. In this case, h, your error, is pi squared minus 10, which, according to our computation, is about negative 0.14. All right, so in that case, pi to the 20th, which is pi squared to the 10th, is approximately 10 to the 10th plus the derivative of x to the 10th, that's 10 times x to the 9th, evaluated at x equals 10, times h, negative 0.14. Now, if we simplify that a little bit, we see that we get 0.86 times 10 to the 10th, or 8.6 times 10 to the 9th. That's our approximation to pi to the 20th. In scientific notation, that would be 8.6 E9. The true answer is approximately 8.77 E9. We're not terribly close, but we at least got the number of digits correct and the first digit correct as well. We're within 2%. Now, I can hear you wondering why we don't simply use a calculator. But what is the calculator doing? How does the calculator compute a number? Well, the calculator is using linear approximation as well, often through the following algorithm. Newton's method is an algorithm for finding the root of a function, f of x. The first step in this method is to guess. Pick some value, let's call it x, where we can compute the function and its derivative. Then let's say that the root is nearby at some value x plus h for some h. We're going to linearize f at x to get f at x plus h equals f of x plus f prime at x times h plus terms in big O of h squared. Ignoring those terms and approximating, we can solve for the root. Set that equal to 0 and solve for h. And that gives us minus f of x over f prime at x. Now h is not the root. X plus h is the root. And so we get the following formula. And the genius of Newton's method is not to stop there, but to repeat or iterate and do it again, getting a better approximation. And then your last step is to hope that this repetition will converge to the desired root. So, if you zoom in on what's happening, we linearize, solve for the root. Then we do it again. We linearize at that new point and then solve for the root. Keep your fingers crossed. This may converge. Now, let's introduce a bit of notation. Our initial guess we will call x naught, that is x with a subscript 0. Doing the linearization and solving gives us an update rule. x1 is equal to x naught minus f at x naught over f prime at x naught. And the repetition gives us a sequence of points x sub n, where the next term in the sequence, x sub n plus 1, is given by x sub n minus f of xn over f prime at xn. This is Newton's method. Now, hopefully, it converges. Let's consider the problem of trying to compute the reciprocal of a number, a. 1 over a can be realized as the root of f of x equals a minus 1 over x. What would it take to compute that root? Well, the derivative of this function is easy to compute. It's 1 over x squared. And taking Newton's update law, substituting in for f and f prime, and doing a little bit of simplification, gives that x n plus 1 equals twice xn minus a times xn squared. What's remarkable in this formula is that there's no division involved, only multiplication and subtraction. So let's fire up the computer and see if we can't solve this for a value of a equal to e, 2.71828, etc. We'll make an initial guess of x naught equals 1/2, and then we'll start computing using Newton's update law that we have derived. And what we see is that after a few short steps, just 4 steps, seems to be giving us 6 digits of accuracy. That's pretty good convergence. Likewise, if we want to compute a cube root of a, we can realize that as the root of f of x equals x cubed minus a. In this case, also, the derivative is trivial to compute. And inserting these into Newton's update law gives us xn plus 1 equals 2/3 xn plus a over 3 times xn squared. Now again, if we, say, evaluate this for a equals 100, what's the cube root of 100? We need to make a guess. I know that the cube root of 125 is 5. So let's use that for our initial guess. And then doing the computations gives a value that seems to be converging extremely quickly. Even after 3 steps, we've got as many digits of accuracy as represented on this computer. So what we see is that sometimes Newton's method converges very quickly. But other things can happen. You have to be careful. Let's say you pick an initial condition and start applying Newton's method. One of the things that can happen is that you do not converge to the root you wanted to get. You may converge to a different root. Worse things can happen still. Depending on your initial condition, you might wind up getting a value of xn for which the derivative there vanishes. As you can see, either graphically or from the update law, this leads to a situation where xn plus 1 is undefined. And this is really bad. You might not converge to anything. But despite those dangers, Newton's method and linearization are extremely useful in practice. Linearization pervades mathematics, and there are all manner of things that you can linearize. You can linearize data. You can linearize differential equations and dynamics. You can even linearize operators. We'll get to a little bit of this later on in this course, but some of it is going to have to wait for you to take more math.
And so we see the power of linearization, of using the first derivative to approximate. But this is really just the first step in a broader Taylor expansion. In our next lesson, we'll consider higher derivatives and their uses across a variety of applications.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 13 on higher derivatives.
In single variable calculus, the derivative of a function is another function of the same type. Therefore, one can iterate the construction, computing rates of change, of rates of change, of rates of change. In this lesson, we'll consider such higher derivatives from the point of view of physical applications, considering examples covering race car driving to robotics to ocean waves.
You know, and I know, what happens when you differentiate a polynomial and when you keep differentiating a polynomial. Higher and higher derivatives give you deeper information, but polynomials are finite, and that means that eventually derivatives will annihilate a polynomial and send it to zero. Higher derivatives come with a number of different notational conventions. You may be tempted to write f prime, f double prime, f triple prime, etc. This is not so good in general. It might make your homework a little bit confusing to read. A bit better notation would be that which we used for Taylor series, denoting the nth derivative of f using a superscript n in parentheses. Better still is the notation df dx, d squared f dx squared, d cubed f dx cubed, etc. But this leads to the question, why is that notation used? Why is the second derivative not df squared, dx squared? Of course, the reason is that we're taking powers of the differentiation operator, d by dx. Where are these higher derivatives to be found? How do we interpret them? One good example comes from dynamics. If x, as a function of time t, denotes the position of a moving body, then one interpretation for the first derivative is as velocity, as I'm sure you've seen before in your introductory physics. You may also know that the second derivative of position is, indeed, acceleration. It is the rate of change of velocity. What about the third derivative of position? What is that? What about the fourth derivative? And higher still, do these have physical meanings? Well, they certainly do. The third derivative is sometimes called jerk. The fourth derivative, depending on which side of the ocean you're on, is either called snap or jounce. Now, maybe you've heard of these before, maybe you haven't. When might you need to know something about this? Well, if you're working with any sort of interesting system involving dynamics, A good example would be the quadrotor robots that can fly extremely precisely. From what does that precision come? It comes from careful control, not only of velocity and acceleration, but of jerk and snap as well. There are other interpretations for higher derivatives as well. One interesting interpretation comes from geometry and curvature. What is curvature? Well, you can certainly feel curvature when you're driving down the road and you make a sharp turn. You can tell the difference between a looser and a tighter sort of turn. The higher the curvature, the more you feel when you turn. But what is curvature really? Well, it seems from this physical explanation to have something to do with radius. If we had a circle that was tangent to our road, the point at which we're turning, then the radius r of that circle would seem to correlate somehow to the curvature that you feel as you go around. The smaller the radius, the higher the curvature. And indeed, at a point on a curve, one definition for curvature is as the reciprocal of the radius of the osculating circle, the circle that agrees with that curve to second order. We're going to do a somewhat lengthy derivation to get a formula for curvature. Consider a function, y equals f of x, and let's fit to it a circle that agrees up to second order. We'll say that the radius of that circle is some unknown, r, and we'll set up a coordinate system, x, based at the center of that circle. Now, at some value of x, the graph of this circle, that is square root of r squared minus x squared, is going to agree with f and its derivatives, at least the first two. Now, let's do a little bit of work. If we differentiate this equation, what do we get? We get f prime is equal to what? Well, we have to take the derivative of r squared minus x squared to the 1/2. That's 1/2 r squared minus x squared to the negative 1/2 times the derivative of what's on the inside, negative 2x. There's a little bit of simplification that goes on, and we get negative x times quantity r squared minus x squared to the negative 1/2. Now, this has to agree to second order, so let's compute another derivative. On the left, we get f double prime. On the right, what do we get? Well, we're going to have to use a product rule. First of all, we have minus quantity r squared minus x squared to the negative 1/2. Then we have plus negative x times the derivative of r squared minus x squared to the negative 1/2, which gives us a negative 1/2, then an r squared minus x squared to the negative 3/2, and then a negative 2x factor. There's a little bit of simplification we can do here by factoring out a negative r squared minus x squared to the negative 3/2. What we're left with is an r squared, a minus x squared, and a plus x squared. The negative x squared and the plus squareds cancel, and we're left with a r squared that we put out in front. So f double prime is negative r squared times quantity r squared minus x squared to the negative 3/2. Now let's step back for a second. At the point of tangency, we know f prime and f double prime. What we don't know are the values of x and, most importantly, r. That's two equations, two unknowns. We ought to be able to solve for r and get the curvature. Let's do some manipulations. Taking the first equation and squaring it gives us, on the left, f prime squared. On the right, negative x squared, that is, positive x squared, times r squared minus x squared to the negative 1. Now, if we rearrange that a little bit and then multiply through the f prime squared by the quantities on the left, we get f prime squared times r squared minus f prime squared times x squared equals x squared. If we rearrange again, factor out the x squared term, then solving for x squared gives us x squared equals f prime squared times r squared all over 1 plus f prime squared. Now, we can substitute that into the second equation, the equation for f double prime, and so eliminate the x variable. When we do that substitution, what are we going to get? We'll get that f double prime equals negative r squared times r squared minus f prime squared times r squared over 1 plus f prime squared, all of that to the negative 3/2. Well, we can factor out an r squared from that term on the right, do a little bit of algebraic simplification, and then some canceling of the r squareds, and we'll get that f double prime equals negative 1 over r times quantity 1 over 1 plus f prime squared, all to the negative 3/2. Once we get that, then it's not going to be hard to solve for r. We'll get rid of that pesky negative sign by taking an absolute value, and then solving for 1 over r gives the curvature kappa to be the absolute value of f double prime over quantity 1 plus f prime squared to the 3/2. That's a complicated derivation and a complicated looking formula, but it's a very general formula for computing curvature. Now, how might we use this? Well, first of all, notice that curvature depends only on the first derivative and the second derivative. That makes sense since it's being captured by something to do with a circle and second order tangency. If we were in a setting, let's say looking at ocean waves, where the derivatives were fairly small, then we could approximate the curvature by saying it's f double prime times what? Well, if f prime is small, we can use the binomial series to expand it as 1 minus 3/2 f prime squared plus some higher order terms in f prime. You could work out what those are. There are a few other things that we see from this formula, namely that the curvature is exactly equal to the second derivative at the maxima or the minima of a curve where f prime equals 0. That's probably something that you want to remember. Curvature is really just the second derivative when you're talking about a max or a min. There are some other things that come out of this formula, namely that the curvature is 0 at an inflection point. And, as you might have already guessed, the sign of this second derivative determines the concavity of the graph, whether it's concave up or concave down. Yet another physical interpretation of higher derivatives comes in the subject of elasticity. Consider a deformable beam with a uniform cross-section and some static load, a weight that is applied that may vary with position x along the beam. What one often wants to know is how much does the beam deflect? This deflection, u, as a function of position, x, satisfies the following equation. The fourth derivative of the deflection is proportional to the load. Now, there are some constants of proportionality involved. One of them, E, is an elasticity based on the material the beam is made from. The other constant, I, is a moment of inertia related to the cross-section. You don't have to know what any of that is. We'll talk a little bit about moments of inertia later in the course. For now, the thing to know is that it's the fourth derivative of the deflection that matters in this elasticity problem. But of course, our final interpretation for higher derivatives is in terms of Taylor series, that they provide the means to get better and better approximations to functions.
Derivatives and iterated derivatives really are everywhere and all about. But what are they good for? In our next lesson, we'll consider one of the great applications of higher derivatives to optimization problems.
Welcome to Calculus. I'm Professor Greist, and we're about to begin Lecture 13, Bonus Material. In our main lesson, we saw that perhaps the ultimate interpretation of higher derivatives is in terms of Taylor series, that if we are at a particular input, then the more derivatives we know at that input, the better we can approximate what the value of the function is farther away by some step h. It's a bit remarkable that just by knowing infinitesimal information at a particular input, that is, higher and higher derivatives at a, you can say what the function is doing far away. That actually goes fairly deep into other areas of mathematics. Let's take a few minutes and think a bit. In what follows, I'm going to use the language of operators, where, for purposes of this course, an operator is something that takes as its input a function and returns as its output another function. What are some examples of operators? Well, there's one that we've been looking at rather closely. The derivative. I'm going to give it an operator symbol as a capital D. Then what does capital D do? It takes a function f and returns the derivative df dx. Now, what's so special about this? Well, operators have an algebra associated with them. For example, we can take d and raise it to certain powers. We can talk about d squared as meaning we apply d twice. You take the derivative, then you take the derivative again. So the operator d squared is really taking the second derivative. D cubed is taking the third derivative. What is d to the 0? Well, that too has a name. It is called the identity operator and is given the special symbol I. The identity operator takes f and returns f. It does nothing. That is why it is called the identity. So d to the 0, the 0th derivative of f is, of course, f. What happens when we take powers of I? Well, I squared means do nothing, I, and then do nothing again. So I squared is equal to I. This might remind you of a number with which you're somewhat familiar. That is the number 1 under multiplication. 1 times 1 is 1. I squared is equal to I. This identity operator plays the role of the number 1 in the algebra that will follow. There are a few other interesting operators that we're going to take a look at. One, let's call it E, capital E. This corresponds to a shift of f. E of f is going to be the function which, when evaluated at x, gives you f at x plus 1. This has the effect of shifting the graph of f to the left by 1 unit. Now, what happens when we take e squared? That means shift to the left by 1, then shift to the left by 1 again. We can talk about e cubed, e to the 4th, etc. We're continually shifting f to the left. Now, can you talk about e raised to a non-integer power? E to the h. Well, surely that makes sense. We can simply evaluate f not at x, but at x plus h. And this means, of course, that we can talk about e to the negative 1, which we would call a right shift. Instead of evaluating f at x plus 1, it evaluates f at x minus 1. But note that this right shift, e inverse, really is the inverse of e. If I multiply e to the negative 1 times e, I get e to the 0, or the identity operator. Of course, this works whether I multiply e inverse by e or e by e inverse. This means that I now have a nice language for doing algebra with these operators. Let's see what happens when we think in this language for a little bit. What is e to the h of f evaluated at x? This is a shift by h. I need to take f and evaluate it at x plus h. Now, let's use our intuition from Taylor series. If I take the Taylor expansion of this, it is the sum, k goes from 0 to infinity, of 1 over k factorial times the kth derivative of f evaluated at x times h to the k. Now, for the moment, let's not worry about where we evaluate this so much. Let's try to rewrite this in the language of operators. Now notice there's a kth derivative of f. So let's use our differentiation operator, d to the k, for taking that kth derivative of f. And now we see that there are two terms that are raised to the kth power, d, the differentiation operator, and h, this perturbation to the input. So if I collect those two terms together and say, I've got the sum, k goes from 0 to infinity, of 1 over k factorial times quantity hd to the k. I apply that to f and evaluate it at x. That is what this shift is. Now, step back for a moment and take a look at what we've done. We've really said that this operator, e to the h of f, is equal to the sum, k goes from 0 to infinity, of something to the k over k factorial applied to f. What is that? Where have I seen something like that before? This really looks like an exponential. But what am I exponentiating? I am exponentiating h times d, the differentiation operator, and applying that to f. If we remove the dependence on f, then what we see is that this shift operator, capital E to the h, is precisely the exponentiation of h times the differentiation operator. That is really a deep observation, that the shift E, just moving to the left by 1 unit, is I plus d plus 1/2 d squared plus 1 over 3 factorial d cubed, etc., etc. The shift is the exponential of the differentiation operator. Or, if you like, you can think of the differentiation operator d as the natural logarithm of the shift operator. Now, this probably is causing a little bit of surprise or confusion. What's going on? Well, don't worry too much. But think back to how this course began. We asked the question, what is e to the x? We will continue asking this question throughout the semester. What we have seen is that there are many responses to this question and many layers of understanding what we mean by exponentiation, what we mean by differentiation, and how derivatives conspire to give you deep information about a function. Welcome to Calculus. I'm Professor Greist, and we're about to begin Lecture 14 on optimization.
One of the best applications of derivatives is to a class of problems you may have called max-min. The modern terminology is optimization. In this lesson, we'll use derivatives to compute maxima and minima for optimization problems, solving some that are simple and some not so simple.
Optimization theory is a wonderful class of problems to which calculus applies. In optimization, you ask, what is the best? How do you maximize profit? How do you minimize drag on an airplane wing? How do you find the best route through a complex network? These are all aspects of optimization. A simple question to which calculus can be applied is, given a function, what is its maximum or minimum value? Well, I'm sure you've seen something along these lines before, but let's step back and think for a moment. If we have a function and we take a close look at its graph, then one of the things that we can observe is that if we are at a place where the derivative is non-zero, then we are certainly not at a maximum or a minimum, because if we zoom in and look at the local behavior at a point where the derivative is not zero, then because derivatives connote rates of change, then if the derivative is negative, that means the function is decreasing locally. On the other hand, if the derivative is a positive value, then the function is increasing locally as we increase the input. Now, of course, we can run that observation in reverse. If we do have a maximum or a minimum, and the derivative exists there, then it must be equal to zero. This motivates the following definition. A critical point of a function f is an input, a, at which the derivative vanishes. So, for example, if we look at a location where there's a minimum, that's a critical point. If we look at a location where there is a maximum, that, too, is a critical point. However, there are critical points that are neither maxima nor minima, such as an inflection point. And, in general, the collection of critical points for a function is strictly larger than the collection of extrema, places where you have a max or a min. Now, things are a bit more complex than this, really. What happens if we have a function that is discontinuous, or not differentiable at a point, or not defined at a certain input? Well, a lot of different things can happen. Maxima, minima, neither. We want to expand our definition of a critical point to include as well those locations at which things go bad, such as where the derivative is undefined. The classification of critical points into maxima, minima, or neither is subtle. You may recall the wonderful second derivative test that is so helpful. Recall that at a critical point, x equals a, you have a minimum if the second derivative at a is bigger than 0. You have a maximum if that second derivative at a is less than 0. If your second derivative is 0 or is undefined, then you have a fail. The test does not tell you whether it's a minimum or a maximum or neither. Now, these are only local minima or maxima, since you're just using derivative information. And some students get things mixed up. What do you do? Is it positive for a minimum or positive for a maximum? Negative? Which is it? I'll leave it to you to come up with a way to remember how this goes. Now, why is it that the second derivative test works? Well, as with the case of L'Hopital's rule, there's a good reason, and Taylor series allow us to see that reason transparently. Consider what happens at a critical point x equals a. If we Taylor expand f about that point, then what can we say? Well, because we have a critical point, the first derivative vanishes. Then, with that gone away, and ignoring all of the higher order terms, that is, terms of degree 3 and greater, what do we see? F looks like a quadratic. You have a constant term, and then the leading term after that is quadratic in x minus a. That means, ignoring the higher order terms, that the graph looks locally like a parabola. That parabola would open up if the coefficient in front of the second degree term is positive. That would open down if the coefficient is negative. Therefore, we see that the sign of that second derivative at a tells us whether we have a local maximum or a local minimum. Let's consider the simple example, sine squared x times log of cosine of x. This has a critical point at x equals 0. What happens when we Taylor expand? Sine of x becomes x plus big O of x cubed. We square that and then multiply it by the log of what? Well, 1 minus x squared over 2 plus big O of x to the 4th. We have a little bit more expansion to do, taking the sine squared term and expanding that out, and then expanding log of 1 plus something into, in this case, negative x squared over 2 plus big O of x to the 4th. Now, when we multiply these three expansions out, the leading order term is given by the product of x and negative x squared over 2. That is, we get a negative 1/2 x to the 4th plus big O x to the 6th. And we can see why we didn't use the second derivative test here, because it would have given us a 0, a fail. However, we can conclude that this really is a local maximum at 0 because of this coefficient of negative 1/2 in front of the x to the 4th. So what does that mean? Have we just invented the fourth derivative test? No, nothing that exciting. We've just done Taylor expansion. Instead of relying on specialized tests, rely on the principles. In this case, Taylor expand to see what's happening. Let's do a simple example. Consider a square of side length L, out of which we cut the four corners. We remove 4 squares of equal size and then fold at the internal edges to get an open-topped box. I want you to maximize the volume of that box with respect to what we remove. If we remove larger squares, we might get a smaller volume box. If we remove smaller squares, then we might get a smaller volume box. What is the maximal volume? Well, in this case, we'd better set x to be a variable. in this case, the side length of the corners that we remove. Then, in this case, the volume is what? Well, when we fold it up, the height of the box is x, and the length of the base is quantity L minus 2x. So the volume is x times L minus 2x quantity squared. Multiplying that out gives 4x cubed minus 4L x squared plus L squared times x. Now remember, x is the variable and L is a constant, so that when we differentiate with respect to x, we get 12x squared minus 8lx plus L squared. This factors nicely as 6x minus L times 2x minus L. And we want to factor that because we're going to compute the critical points, setting that derivative equal to 0. Solving gives us two critical points, one at x equals L over 2, and the other at x equals L over 6. We must classify these as maxima or minima, or neither, as best we can. So we'll take the second derivative, which we can compute to be 24x minus 8L. Evaluating that second derivative at the critical points gives us what? At L over 2, it gives us 4L. That's a positive number, and that means that we have a minimum, or a local minimum, at that point. At x equals L over 6, the second derivative is negative 4L. That gives us a local maximum. Of course, this fits with your intuition. If x is equal to L over 2, then what is happening when you fold up that box? Oh, well, you're getting something with volume 0. That's clearly a minimum. We therefore conclude that the volume is maximized at x equals L over 6. But notice the problem is asking us for the maximum volume, not the value of x at which the volume is maximized. So we need to substitute back in x equals L over 6 into v to get 2L over 3, that's L minus 2x, squared times x, or L over 6. Simplifying that gives us 2L cubed over 27. That is the maximal volume. Let's look at another example. In this case, extremize the function f of x equals x cubed over 3 minus 3x squared plus 8x minus 2. And here the extremization is with some constraint. Namely, we want x to be bigger than or equal to 0. So no negative values. Let's proceed the same way. We compute the derivative of f. And we get x squared minus 6x plus 8. To compute the critical points, we're going to want to factor this as x minus 2 times x minus 4. And so setting that equal to 0 gives us a pair of critical points, x equals 2 and x equals 4. To classify them, let's compute the second derivative of f. That is simply 2x minus 6. And so we see that at x equals 2, we have a maximum with a value of 14/3. At x equals 4, the second derivative is positive, so we have a minimum at a value of 10/3. However, that is not the end. These are local extrema. The problem is to find the global maximum and minimum. When you're asked to find a global max or min, you must check the endpoints of your domain. These endpoints are critical points, since the function and or its derivative may not exist there. Let us therefore check the endpoints of our domain. Remember, our constraint is that x must be bigger than or equal to 0. Therefore, the left-hand endpoint is at x equals 0. What do we see there? Well, the value that the function takes on is -2. This is a minimum since it is less than the other critical values that we have computed. In fact, this is the global minimum for the function. Are there any other critical points that we have to look at? Well, there's not really a right-hand endpoint to the domain, since it is unbounded. But if we tweak the language a little bit, we can say that infinity is a critical point. What is the function doing at infinity, or more properly, as x goes to infinity? Well, you can see that because the leading order term is x cubed over 3, the function tends to infinity. And therefore, we have a maximum, a global maximum, taking on the value of infinity at this right-hand endpoint. Now, of course, all of this would be fairly obvious if you drew the graph of the function. You would see the difference between the local max and the local min that we have computed and the global minimum and maximum at the left and right-hand endpoints, respectively. Always check your endpoints.
This lecture was the best, or maybe it was the worst. You're going to have to compute a few derivatives to find out for sure. In our next lesson, we're going to turn from the concrete notion of a derivative to the subtly different idea of a differential.
Welcome to Calculus. I'm Professor Greist, and we're about to begin Lecture 14, Bonus Material. Let's consider a more involved example, this one motivated by a problem in statistics. Let's say that you run an experiment and it gives you some data that is of the following form: y equals m times x. That is, you measure x values and y values, and you know that there's some linear relationship between them, but you don't know the value of m. Perhaps this is coming from a physical experiment, like trying to measure a spring constant by measuring force and deflection. Whatever the physical motivation, you are given some collection of data points, but these data points are noisy. They don't fit perfectly on the line. How do you determine the appropriate value of m? Well, you could just draw a line and try to make it fit and look right. But wouldn't it be nice to have a more principled approach? This is what statistics is meant for. So let's assume that the inputs to your problem are a collection of data points: x values, x sub I, and y values, y sub I, that are paired. Now, in order to find the appropriate value of m, we're going to write this as an optimization problem. The method of least squares is a wonderful technique for determining the optimal m. Consider the function s, depending on m, that is given by the following. I'm going to look at the vertical distance between the data points and the line of slope m. This vertical distance is given by y sub I minus m times x sub I. What I'm going to want to do is add up all of those distances and then minimize. Now, there's a bit of a problem in that these distances are signed. They're positive or negative, because I'm really just looking at the change in y values. So let's square that term. We have y sub I minus mx sub I, quantity, squared. And now let's sum all of those terms up over I. This is going to give you a deviation of the data from the line of slope m. This function depends on m. If we chose a value of m like 0, well, that would give a very large value of s in this case. What we want to do is find the value of m that minimizes this deviation s. So let's proceed. If we compute the derivative of s with respect to m, what will we get? This looks scary, but it's not so bad. Differentiation is linear, so we can pass the derivative inside the summation sign. Now, using the chain rule, what do we get? Well, we get twice quantity y sub I minus m times x sub I times the derivative of that quantity with respect to m. That derivative is negative x sub I. Now, if we distribute this multiplication and expand out into two sums, we get minus 2 times the sum over I of xi times yi plus 2 times m times the sum over I xi squared. We can factor out that 2 and that m because they appear in every summation term. Now, our goal is to compute the minimum, so we find the critical point by setting this derivative equal to 0. Moving one sum over to the other side, we see that 2 times the sum over I of xi yi is equal to 2m times the sum over I of xi squared. What is it that we're trying to solve for? We're trying to solve for m. And so, canceling the 2's and then dividing both sides by the sum of xi squared gives a value of m equal to the sum over I of xi times yi divided by the sum over I of xi squared. The question remains, is this critical point a local min or a local max? Well, you might guess that it's a local min, but how would you show it for sure? Well, if we compute the second derivative of s with respect to m, what will we get? It looks complicated, but there's really only one m in that first derivative. And so, treating everything else as a constant, we get that the second derivative is simply 2 times the sum over I of xi squared. What do we note about that? We don't care what the xi values are. When we square it, we get something non-negative. So as long as some of the xi terms are positive, we get a positive second derivative and a minimum. This value of m is going to minimize our deviation and give us a best fit line. Now, what happens if our experiment is a little bit different? The line that we're looking for doesn't necessarily pass through the origin. Well, it doesn't seem as though the problem has really changed much at all. We're just, again, looking for a straight line. But now we have to worry about not only the slope, but also the y-intercept, which we might call b. We're looking for a line of the form y equals mx plus b. I wonder, could we do the same thing? Well, the vertical distance would involve a b term in this s function. And now, this function would depend not only on m, but on b. And this leads us to some very interesting questions because we do not know how to find a max or a min of a function that depends on more than one input. This is really a problem that you're going to come back to in multivariable calculus when you have functions with several inputs. How do you do optimization? Well, I've got to tell you, some unusual things can happen in that context. But those unusual situations wind up opening a whole new world of interesting questions and applications. For example, game theory deals with optimization of multivariate functions. Linear programming, machine learning, all of these fascinating subjects are deeply concerned with optimization, with finding maxima, minima, and other types of critical points. There are some wonderful fields out there that will rely on the intuition that you've learned in single variable calculus. Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 15 on differentials.
We begin this lecture with a question. What is dx? You may have been waiting your whole life to find out, but you're not going to get a complete answer right now. Sorry. But along the way, we'll learn enough about differentials to be able to answer some important questions about geometry, physics, and economics.
So, what exactly do we mean when we write dx or du? They're used all the time in calculus class. One perspective is that they're infinitesimals, really, really small bits of x or u, so that when you integrate du, what you get is u. That's a reasonable intuition, but is that really what they mean? Maybe they connote a rate of change, so that, according to the chain rule, du and dx are related by du dx, meaning that if du connotes the rate of change of u and dx the rate of change of x, then they are related by du dx, the rate of change of u with respect to x. That's a reasonable interpretation. It's not the full truth. The full truth is that these are differential forms. We are not, however, going to cover that in this single variable course. For now, let's think about what d is doing. D is an operator, which means that if you put in a function, f, you get out df, this differential that is telling you something about rates of change of outputs with respect to inputs. Now, the fact that it's an operator means that we can differentiate an equation, something of the form f equals g. And what we will get out is again an equation, df equals dg. Now, you've probably seen this before. It goes under the name of implicit differentiation, and it's extremely useful. For example, if we want to know the slope of the tangent line to a circle of radius r centered at the origin in the xy plane, then what would we do? We would write down the equation of that circle, x squared plus y squared equals r squared, and then we would differentiate the entire equation. Applying the d operator gives us what? D of x squared is 2x dx. D of y squared is 2y dy. What is d of r squared? Well, if r is a constant, then dr would be equal to 0, or if you like, differentiating a constant gives you 0. This equation, then, involving the differentials dx and dy, allows us to solve for the slope of the tangent line, dy dx. Using a little bit of algebra, we get that it is negative x over y, a result that you can clearly see. let's turn to an application in economics. This one dealing with substitution rates. In economics, the marginal rate of substitution of a product X for a product Y is the rate at which a consumer is willing to exchange the good or product Y for the good X. This assumes a fixed utility. I don't want to go too much into economics here, but let's take a moment and explain what this means. This marginal rate of substitution, MRS, can be expressed as minus dy over dx along a curve of fixed utility, u. So let's say we're looking at the xy plane. I have some utility function, u. When we set that equal to a constant, it gives us a curve in the xy plane. The marginal rate of substitution is related to dy dx, the slope of the tangent line. Let's make this a little more specific. Let's say that x is the amount of coffee I have, y the amount of donuts that I have, and my utility function, u, is y squared times quantity, x minus 3. In this case, differentiating that equation gives me du equals d of quantity y squared times x minus 3. Now, since I'm along a fixed utility curve, u is a constant, so du is 0. And on the right, applying the product rule, I get 2y dy times x minus 3 plus y squared times dx. And now, solving for the marginal rate of substitution, that is minus dy over dx, gives me negative y squared over 2y times quantity x minus 3. We can simplify, removing the negative signs and the y's, and we get a marginal rate of substitution of y over 2 times quantity x minus 3. Now, what does that actually mean? What that actually means is that depending on my values of x and y, how much coffee I have versus how many donuts I have, my willingness to trade one for the other changes. If I have an equal amount of coffee and donuts, then that's one thing. I might be willing to trade one for another. However, if the amount of coffee that I have is sufficiently low, that is, x is close to 3, it doesn't matter how many donuts you're willing to give me. I'm not going to give up any more coffee. Differentials often arise in related rates problems. Here's a fun one. Let's say that you have water flowing from a faucet in a smooth stream. What I'd like to know is, how does the cross-sectional shape change? It seems as though the stream gets thinner as you go. Let's assume that the cross-sectional shape is circular. We'll try to see what happens to the radius of that circle. We'll start from the assumption that we have a steady stream, which means that the flow rate through a cross-section must be constant. What is the flow rate? Well, that's the area times the velocity at that slice. If that's a constant, then we can write that equation as pi r squared v equals c, where r is the radius and v is the velocity. Differentiating this equation yields what? Well, we're going to ignore the pi, absorb that into the constant on the right, and then, using the product rule, we get 2r dr times v plus r squared times dv equals 0. Now we can do a little bit of algebra to get our hands on dr. That is negative r squared over 2rv times dv. We can simplify that, canceling the r's, to negative r over 2v dv. And now, let's say we wanted to know how that radius is changing with respect to time. The time rate of change would be dr dt, which we can write as negative r over 2v times dv dt. What can we say now to simplify things? Well, since dv dt is a constant, since the water is falling under the influence of gravity, dv dt is exactly g. And so we get dr dt equals negative r times g over 2v. We could simplify that, knowing what we know about v, to negative r times g over 2 quantity v naught plus g times t, where v naught is the initial velocity coming out of the faucet. That still doesn't tell us exactly what the shape is, say, as a function of height, but we could either solve that differential equation or use some conservation properties from physics to get that shape if we wanted. We have manipulated the differentials to give us information about time rates of change. A related concept is that of a relative rate of change. A relative rate is a normalization of the differential, something of the form du over u. This is telling you something about what percentage change you have. Notice it is unitless, and notice you could also get it in terms of the log of u. Let's put this idea to work. If we have a voltage across a variable resistor that is fixed, then how are the relative rates of resistance and current related? So in a simple circuit with voltage potential V, current flow I, and variable resistance R, these quantities are related by Ohm's law. That is, V equals I times R. Now, if we differentiate both sides of this equation, we get dV equals R dI plus I dR. And now, to compute the relative rate of change, we look at dV over V. That must be 0, since the voltage is fixed. So, dividing the right-hand side by V gives us what? Well, RdI plus IdR over I times R. That splits up into dI over I plus dR over R, meaning that the relative rates of change of R and I are inversely related. Let's look at an example from geometry. How does the relative change in volume relate to that of surface area? In the specific case of a solid ball of radius r, how do the volume and the areas compare? Well, the volume is 4/3 pi r cubed. When we differentiate that, we get dV equals 4 pi r squared dr. Now, for surface area, that function is 4 pi r squared. Differentiating that gives dA equals 8 pi r dr. Now, to look at the relative changes, we must take dV over V and divide that by dA over A to compare these relative rates. What is that? Well, that is going to be 3 dr over r over 2 dr over r. With a little bit of algebra, you can see that it's a constant, 3/2. I wonder if that holds for any other shapes. Let's take a cube of side length s. The volume of that cube is s cubed. When we differentiate, we get dV equals 3s squared ds. The surface area is 6s squared. Differentiating yields dA equals 12s ds. If we again look at dV over V and compare that to dA over A, we're going to get 3 ds over s over 2 ds over s. The relative rates of length cancel, and we get, again, 3/2. That means the relative volume change is always 150% of the relative area change. I wonder if that has any meaning. Well, let's go back to economics and consider the important questions. That is, what is the difference between milk and wine? Well, it is in elasticity of demand. If P is the price and Q is the quantity demanded at that price, then the elasticity, E, is defined to be the rate of change of the relative demand with respect to the relative price. That is, dq over q divided by dp over p. We're going to put a minus sign in front of this since price and quantity are inversely related. When we do so, what do we see? Well, the higher the price is, the less you want something. The lower the price, the more you want. But it depends on elasticity. If E is between 0 and 1, we say that demand is inelastic. Changes in price don't change the quantity demanded so much, like milk. On the other hand, if E is larger than 1, then this is called elastic demand. If wine goes on sale, I'm more likely to buy more and then store it. That doesn't work with milk. Now, when E is equal to 1, it is called perfectly elastic. Note that it is not slope, but rather relative rates of change. Here's a question. How do you maximize the relative revenue with respect to relative change in price? Well, R, the revenue, is the price times the quantity, P times Q, or the area of this box, if you like. Then, differentiating this, we get dr equals P dq plus Q dP. Looking at relative revenue is dr over R. We've seen a very similar computation with our electric circuit. We get dq over Q plus dP over P. And now, looking at the ratio of relative revenue to relative price gives us what? dq over Q over dP over P plus dP over P over dP over P. That latter term simplifies to 1. The former is negative E. So we have maximal revenue when the elasticity equals 1. So, concluding, what do we mean by dx and du? There is much more to the story than what we have said. For now, differentials are functions that implicate rates of change. When you get to multivariable calculus, you'll learn a different perspective involving differential forms.
We've seen in this lesson that thinking of derivatives from a more abstract perspective, that of differentials, is very useful in several application domains. We will continue this process in our next lecture by thinking of differentiation itself as an abstract operator. In this more rarefied setting, we'll see that it deepens our understanding and leads to better computation as well as comprehension.
Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 16 on the differentiation operator.
You may have come into this class thinking of derivatives in terms of numbers or slopes, but we've broadened our perspective by thinking in more abstract and conceptual terms. We're going to culminate that process in this lesson by thinking of differentiation as an operator. This more global perspective is going to lead us not only to better comprehension, but better computational abilities.
Some derivatives do not follow from the basic rules that we've covered thus far. For example, what's the derivative of 2 to the x? If you don't recall, you may be tempted to write x times 2 to the x minus 1. That would be a mistake. That is not the derivative. What about some other functions? Arcsine of x. Do you recall the derivative? That. What about x to the x? Or x to the x to the x? Or more complicated functions still. These can be differentiated, but we cannot use the basic rules that we've learned thus far. What we will use is the idea that differentiation is an operator and that it acts on equations as well as functions, and more importantly, it works well with other operators such as exponentiation or integration, taking a limit, or in particular, the differentiation operator works well with the natural logarithm operator. And that is the basis for that method known as logarithmic differentiation. Let's begin with a simple example. Compute the derivative of e to the x. Now, I know that you know what that derivative is, but let us compute this via logarithmic differentiation. The key step will be to write e to the x as y, and then to simplify this equation, we'll apply the natural logarithm to both sides. On the left, we obtain log of y. On the right, log of e to the x, that is, x. And now we can differentiate this equation. On the left, we'll obtain dy over y. On the right, we'll obtain dx. And by manipulating these differentials, we can easily compute dy dx to be y. That is e to the x. Now, this process is simple enough, but step back and think of what you're doing. What we're really doing is taking our initial equation and applying the natural logarithm operator and feeding the results of that into the differentiation operator. That is what allows us to compute this derivative. Now, you can compute other things similarly. For example, you could show that the derivative of a to the x, where a is a constant, is a to the x times log of a. That's a fun exercise. But there's more to logarithmic differentiation than just this. In fact, applying operators gives lots of examples of things that are not quite logarithmic differentiation, but follow a similar pattern. For example, let's look at the derivative of log of x. Now, we both know the answer to that, but let's apply a similar methodology. We'll let y be equal to log of x, and now, how do we simplify this? Well, we can apply the exponentiation operator and then apply the differentiation operator. So exponentiating this equation gives e to the y equals e to the log of x, that is, x. Now, assuming that we know how to differentiate exponentials, we can apply the differentiation operator. And on the left, we'll obtain e to the y dy. On the right, dx. Manipulating differentials to solve gives 1 over x as the derivative. And so we see that if you know the derivative of log, you can compute the derivative of the exponential. If you know the derivative of the exponential, you could likewise compute the derivative of the log. But that's not all we can do. If asked to compute the derivative of arcsine, how would we proceed? What would the appropriate operator be? It's pretty clear that sine is what we want to use to feed into the derivative. For example, if we let y be equal to arcsine of x and apply the sine operator to both sides, what do we get? Well, on the left, sine of y. On the right, because arcsine is the inverse of sine, we obtain simply x. And now, because we know the derivative of sine, this is going to be pretty easy. We get cosine of y dy equals dx. And manipulating to obtain dy dx, we get 1 over the cosine of y. That is the secant of y. Now that is not exactly the form of the answer that we want, so we need to do a little bit of trigonometric manipulation. Given the right triangle with angle y, since the sine of y is equal to x, we could assume that the opposite side length is x and the hypotenuse is 1, meaning that the adjacent side length is root 1 minus x squared. This allows us to compute the secant as 1 over the square root of 1 minus x squared, and that indeed is the derivative of arcsine. You can derive many other similar results using this same principle. You can compute the derivative of arccosine, of arctangent. You can even compute the derivatives of the inverses to the hyperbolic trig functions, arcsinch, arccosh, and arctanch. And it's not only derivatives that one can compute using these methods. Operators are very versatile and helpful across mathematics. Let's do an example involving a limit. Compute the limit as x goes to infinity of quantity 1 plus a over x to the x power. Here a is a constant. And note the difficulty implicit here. X is going to infinity, so the term within the parentheses is going to 1, but you're raising this to higher and higher powers. You might be tempted to say that this limit is 1 to the infinity, which seems like it ought to be 1, but that is not applicable. Let's see what that limit is. We're going to, as before, let y be defined as quantity 1 plus a over x to the xth power. And before applying the limit operator, we're going to apply something else. In this case, the natural logarithm to pull down that exponent of x. On the left, we obtain log of y. On the right, using what we know about logarithms, we obtain x times the log of 1 plus a over x. Now we have something that we can work with. We're not differentiating. We are taking a limit. On the left is close to something we want to get, the limit of log of y. On the right, we have the limit as x goes to infinity of x times log of 1 plus a over x. Now, how is this helping us at all? Well, the logarithm is in the form log of 1 plus something that becomes very small as x goes to infinity. So we can use our Taylor expansion and rewrite that as a over x plus something in big O of 1 over x squared. That limit is going to be easy to compute. The leading order term is, in fact, a, and that is the limit, not of y, but of log of y. And so, exponentiating this equation and exchanging with the limit gives the limit as x goes to infinity of e to the log of y, that is y, is e to the a. And that is indeed what the limit of 1 plus a over x to the x is. Now step back for a moment and look at what we've done. We had a challenging limit to compute, a limit that we could not figure out directly. And so we took an indirect route by applying the natural logarithm operator, then taking a limit, then applying the exponentiation operator. The wonderful thing is that we can exchange these with limits in this case and take the long way around to get to where we want to go. Let's look at another example. This one seems intimidating. What is the derivative of x to the x? We're going to follow the same path as before. let y be equal to x to the x. How do we simplify that exponent? Clearly, the natural logarithm is what we're going to want to use. When we apply the natural log, we obtain on the left log of y, and on the right x times log of x. Now we can differentiate. On the left, we'll obtain dy over y. On the right, using the product rule, we get x over x plus log of x dx. That simplifies a little bit. Doing some algebra gives us that dy dx equals y times quantity 1 plus log of x. Replacing that y with x to the x shows us that the derivative of x to the x is x to the x times quantity 1 plus log of x. Now that was easy enough to compute, but let's think. This function, x to the x, is super exponential. It's bigger than the exponential function. And when we compute its derivative, it's even larger than x to the x. It is of order, big O, x to the x times log of x. Now, if we think about what happens when we differentiate functions and look at their growth rates, if I take something that is super exponential in its growth rate and differentiate it, I'm losing control over the growth rate. The growth rate is potentially much larger, as we saw in the example of x to the x, going to something that was in big O of x to the x times log of x. The moral of this lesson is that no matter how difficult the differentiation problem looks, taking advantage of operators is going to help you with a tricky computation.
And so ends Chapter 2 on differentiation. We've come a long way from thinking about a derivative as a slope. Indeed, we've considered derivatives from the point of view of Taylor series and asymptotics. We've considered differentials and, ultimately, differentiation as an operator. We'll begin our next chapter, Chapter 3, by inverting that operator and looking at integration.
Welcome to Calculus. I'm Professor Greist, and we're about to begin Lecture 16, Bonus Material. Let's turn to a challenge problem and consider the infinite power tower. What is the infinite power tower? I'm so glad you asked. It is x to the 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 x, on and on, ad infinitum. Now, your reaction is likely one of disbelief. What is such a function? What does that even mean? How can that exist? That can't be a real function. Well, not only is it a real function, but we are going to compute its derivative. The way we're going to do so is implicitly. The first step is to give it a name. Let's call it y. How is a name going to help us compute the derivative of this function? Well, let's think for a moment. Instead of giving you an explicit formula for y as a function of x, let's rewrite it as follows. Y equals x to the y. This is an implicit definition where I'm defining y in terms of its relationship to x and to itself. And now, with this as the alternate definition, let's compute the derivative, dy dx. We can use the methods of this lesson to do so. Take the logarithm of both sides of the equation. What do we get? Well, we get log of y equals y times log of x. And now, differentiating both sides gives us what? On the left, dy over y. On the right, using the product rule, we get y over x dx plus log of x dy. And now the rest is just a little bit of algebra. Move terms over to the left, collect, factor out the dy. What's left over on the right is y over x dx. And now, rearranging terms, we solve for dy dx as y over x times 1 over y minus log of x to the negative 1. If you like, you can rearrange the terms a little bit, get y squared over x times quantity, 1 minus y log x. Now, notice, there's no way we're going to be able to solve this as a function of x itself. We can't eliminate those y's completely. We could substitute back in the infinite power tower. That would make our formula a little bit messy looking. But consider how easy it was to do this computation and get a formula for the derivative. Now, we're still not done. We haven't answered the question, does this function actually exist? If it does its derivative exist? Just because you can compute something that seems to be a derivative does not mean that the function is in fact differentiable. There are limits to be computed in order to prove this. Well, we're not going to do all of those details, but if you're curious, it is, in fact, true that this function exists. It is well-defined and differentiable on a certain domain, that domain being x between e to the negative e and e to the e minus 1. The function itself looks, well, a little complicated. It blows up pretty quickly after the value of x equals 1, where the function, of course, takes on a value of 1. And 1 to the 1 to the 1 to the 1 to the 1, etc. But what is perhaps a bit more surprising is that there is some interval around 1 where this function can be analyzed, where its derivative can be computed. You can talk about its Taylor series, etc. In fact, this infinite power tower is related to some very interesting and useful functions you won't normally see in an undergraduate class. The Lambert W function is perhaps the most useful function associated to this infinite power tower. It comes up in certain models of biology and population dynamics. We won't be seeing any of those details or really anything more from this function during the rest of this course. But I want you to be introduced to the infinite power tower. Why? To give you nightmares? Well, no. What I want you to see is that with your mind alone and the tools that you are learning, you can analyze functions that you cannot see or feel. You cannot type the infinite power tower into your graphing calculator. You don't know anything about it except its implicit definition. Yet, you are still able to compute its derivative quickly and simply. That is a remarkable thing. That is what mathematics is all about.